Okay, so we're looking on page 57, and he spent some time, the first, on page 57 and most of 58, talking about approximations, things that would interfere with this projectile motion. And he says, first, we will ignore air resistance, as we have done before. Okay, and so if you throw a ping pong ball in the air, it may not do a perfect parabola because of air resistance. Or if you do something heavier with really fast, the friction is going to increase with the speed. So we're just going to ignore that. Second, gravitational attraction of the Earth decreases with an object altitude. So if you got a projectile going really high and far, like say a nuclear ballistic missile or something from one country to another, the trajectory could be affected by the gravity of the Earth. It gets higher because the gravity is going to be less, the force of gravity. Okay. And look at the picture on page 58. They have a battleship firing guns, and can you see the water? It shows the recoil of the ship. I think that's pretty interesting. And it says that they can land a shell on a target over 23 miles away. And it would be in flight over 1.5 minutes and would reach a maximum height of over 14,000 feet, which is nearly 3 miles. Okay, so they have to, you're trying to hit, so if you're trying to hit a ship a few hundred feet long at a distance of 23 miles, you really need to take all that into consideration. But we're not going to do that. And then a third approximation has to do with the rotation of the Earth, believe it or not. If you're shooting projectile that long range, that could affect it. So we're just going to limit our problems to small scale projectile motion. And then on the bottom of page 58, he starts talking about vector analysis and calculation method, and shows a picture on page 59. And I'm going to redraw that. Whenever you drop something, its velocity at first is going to be actually 0, right, when you hit here. And then after 1 second, it'll be 9.8 meters per second. And then at time equals 2, it's gaining 9.8 seconds every second, right? So at 2 seconds, it's going to be 19.6 meters per second. Okay, so it's got a faster velocity. And then at time equals 3 seconds, I don't know what's that. You add that, you get a 4. Huh? Let's go with that. I know it's almost 30, and so it's even longer, right? This is the velocity vector, and so on. And it gets big pretty fast. You know, approximately 10, approximately 20, approximately 30, approximately 40 is picking up almost 10 meters per second each second. And so, like the next one is going to be, much longer. Time equals 4. But let's say you shoot something horizontally, and it's got some kind of velocity, and let's say we're out in the middle of space, or there's no gravity anywhere, then time equals 1 second, it's still the same velocity. Time equals 2 seconds, it's still the same velocity. 3 seconds, same velocity, right? Object in motion stays in motion in the same direction at the same speed, unless acted on by a force. Here it was acted on by a force, so it changed. Okay, now both of these can be happening at the same time though. Like say we put this here, well, they did it right here on page 59. They start something right here going at this direction. So it's got this horizontal velocity and it's got this vertical velocity. And then a little bit later, it's going faster. actually, let me, how to get it. So it's going to have the same horizontal motion, but more vertical motion. I'm going to do it. Same horizontal, more vertical. So you see here the horizontal is supposed to be staying the same. And if you look at the vectors in the book, they have H's and V's for horizontal and vertical for little subscripts. And if you look at the velocity, like velocity 0h, velocity the V1h, 2h, 3h, 4h, 5h, 6h, those are all, those little horizontal arrows are all staying the same length. You notice that? Even at the very top of the trip. But the vertical arrows start out, it starts out big. This one should have been at the bottom. It looks much better. It starts big, but because that gravity is slowing it down, it gets smaller and smaller. And then at the top, it only has horizontal motion. And then it starts getting vertical motion going downward, faster and faster. Okay, so we're going to be working these projectile motion problems, and we have horizontal and vertical motion to deal with. And you don't deal with vertical motion just as vertical, projectile motion as projectile motion. You have to divide it into its two components. Okay, and if you look in the middle of page 59, it says there's one more key to solving projectile motion problems. The horizontal motion and the vertical motion are linked together by time. Now they're independent of one another. In other words, the velocity of the horizontal velocity is unaffected by the vertical velocity. They're independent of each other. But because they're happening at the same time, like if I shoot a bullet horizontally, because it's falling, that's going to limit how long it can be going out there, right? It's going to hit the ground eventually and stop going horizontally until it hits the ground, and that's because of its vertical motion. So time is what connects them. And then look at the bullets at the bottom of page 59. He says, I found the most common source of incorrect answers is confusing and mixing together the vertical and horizontal parts of your problem. So he wants you to adhere strictly to the following strategy. Set up separate columns on your paper for the vertical and horizontal parts of the problem. We'll do a couple of these and you'll see what he's talking about. He says use subscripts very carefully to distinguish vertical quantities from horizontal quantities. And then in each column, place only data, equations, and variables that belong there. Vertical components, variables, and equations in the vertical column, horizontal items in the horizontal column. And only combine the information in your two columns together by substituting for the time. And then next page. And as mentioned in the problem solving method that we're still using from page 50-51, do not insert numerical values into your equations until you have worked the algebra to the end. Okay. Although, like I said, I'm not as strict on that as he is. So let's look at an example. Example 2.8. Various sources say that the 16th century Spanish 24-pounder cannon fired a cannonball with an initial velocity, or the muzzle velocity, of 891 feet per second. So as it came out of the gun, out of the cannon, it had that much velocity, 891 feet per second. If such a cannon is set at an angle of 27 degrees, how far downrange does the cannonball land, assuming the ground was horizontal? Okay, and so it says, in the parlance of artillery, the term downrange refers to horizontal displacement. We've used the term range in math to mean like the y, how much of the y-axis you're using, right? Okay, it means totally different in physics. Range means how far horizontally you go. Okay, it has nothing to do with x and y. And he says, for simplicity, let's assume the muzzle of the cannon is at the ground. What we can do is maybe say, here's the ground. And maybe there's a hole right here. So we've got this cannon so that it's going to shoot like that. And not only that, but it's going to have, what was it, 27 degrees like that. All right. and it's going to go over and then come back down and hit at the same level. So it's going to have that kind. And as we've talked about a little bit in the past, but if you go back to page 56, flip back over to 56. We use this a little bit on the tests and the problems that we've already worked. The symmetry and the kinematics problem. And what that means is a lot of times you can look at just half of the trip because it's going to go up and then it's going to come down. And what it does on this side is looks identical to what is happening over there. And so you could use a point at the very top of the thing and call that, be final and just be talking about the beginning half. So we're going to do a little bit of that also. Okay, so they want to know how far down it goes. So he sets up, first he gets the given. You've got initial velocity of 891 meters per second. Feet per second. That means. And an angle of 27 degrees. And that's all we're given, right? Okay. We do know acceleration, but we're not going to do that yet. What we're going to do is we're going to set up two columns. I'll do it over here. Keep it vertical on this side and horizontal over here. And so if you look at the vertical motion, it goes up and then it comes back down, right? It goes up and then it comes down. If somebody was looking at it, they were standing right behind the bowling ball and say they didn't have any depth perception, they would see the ball go up and then back down because they wouldn't be able to see the sideways motion, right? And then if somebody's looking over here at it this way, or think about this, say he has a shadow on the ground. And so the sun's up here, and so the shadow just goes straight across at a constant rate. Okay, constant motion that way. Okay. But it's got to accelerate, it slows down and speeds up, coming back down. Okay, so draw the initial component. That's the 891. But I guess we better change that. He converts to meters per second and he gets 271.6 meters per second. Okay, to get MKS units. So this line right here is your 271.6 meters per second. But you're not going to use that for anything other than finding the components. There's your horizontal velocity right there. And then this little component up here is your vertical velocity. There's your initial, like this is initial. So you could say VOH, put the little O there, something like that. And do you remember how to find the components? Cosine and cosine, right? Okay. And so the initial vertical motion, I'll put like that, and then V, I think that OV, yeah, would be V sub O. We want the Y value, right? So we use sine. And sine of theta. So that means we're going to have 891, nope, 271.6 meters per second times the sine of 27 degrees. And he doesn't even put the numbers in yet. Okay. It's starting at ground level. And so he says D0 is 0, the original, and vertical. Oh, I see the thing. Okay, it's going to go up and come back down. So that's what he's saying, the displacement is 0. We do have acceleration, negative 9.8 meters per second squared. We're going to say up is positive, down is negative, or vertical. And then for the horizontal, you use E to the cosine theta. 271.6 cosine of 27 degrees. All right. And so you'll have a value for this and a value for that, and those are the ones you use in your calculations. You won't use this original one that you see in the problem anywhere except to get your components. And also important, what equation did we say we had for constant motion? Remember, there's one equation for constant motion. Yes. D equals BT. That's the only one you can use in this column. Okay. Over here, you've got the other three. You had BF equals BO plus AT. What was the other one? BF squared equals BO squared plus 2AD. I think D equaled BIP plus 1/2 AT squared. You have those equations for vertical. Those are all on your formula sheet. So he focuses in on the time of the vertical, because the vertical motion really is what determines your time. If something's going horizontally, it could go horizontally forever. But since it's going to vertically, it's going to go up and then back down and hit the ground, that's going to affect your time. And so you start out with D vertical equals the initial, let's put the 0, initial vertical over here times the time plus 1/2, and then you have negative 9.8 meters per second squared, and then you have your time squared. And we know that it's going to go up and come back down to its original place, and so that's where this D vertical becomes 0. So you have 0 here, and then you'll have this number in there. So the only unknown is your time. But you got it as a quadratic. You notice that? The good thing about it is, no, it's not. Let's rearrange this. I'm going to leave because I don't have this number solved out yet. Anybody have that 271.6 times minus 27? We have to calculate it out. That way, I'll go ahead and put that in. $123.3 meters per second. Okay, so I say 123.3 meters per second times time. And then, so I'm going to pull this out over on this side. I'm going to subtract from both sides. This whole term. So over here, I'll have negative 123.3 meters per second times the time equals 1/2. I'm going to put this negative out in front, 9.8 meters per second squared, and then times squared. And now you notice you have time on both sides. And so you can divide both sides by the time. The only time that doesn't work is when time is equal to 0, right? Because you can't divide by 0. But we know that it's going to be down here, the time will be something, so it's not, so we're okay with that. And so that will just cancel the square. And then we'll have negative 123.3 meters per second. To solve this time by itself, I'm going to multiply by negative 2. And I'm going to divide by the 9.8. You could have left the negative with the 9.8 if you wanted. It doesn't really matter. Because this is all going to become, when you multiply it, it's going to be positive. And that equals the time. Okay, I'm going to do the number there too. See what I did there? Math? Am I confused? solving for this t here, so I'm multiplying by 2 and divided by 90. I like solving for these numbers ahead of time just so that you can look and see if that seems reasonable. That was 271 and this would seem like 123. Okay, what do you get for this? 25.60. 16 seconds. Or yeah. So does it seem like a cannonball would be in the air for 25 seconds? A long time. He doesn't have it there. You could check her math, but we're going to go with it. Okay. So we've got a time over here. And over here we just have a horizontal velocity. Can you do this math right here too? $242. Yep. 0. So this time is going to be true for both of them. And so we can solve for our distance by multiplying the velocity, the horizontal velocity, times the time, which is 25.16. Horizontal. Hopefully it'll be the same thing he gets. So 89.6. So 89.6 really. That's meters, and then he converts it to kilometers. So 6 kilometers away, I think it would take a while to get near that long. That's pretty good for 16th century artillery, getting that kind of range. So does that make sense, the horizontal, the vertical? And you don't always do this. It depends on what's known and what's unknown as to what equations you use and where you start, and then you kind of have to play with it. It's kind of a challenge. You have to just do a lot of examples. So let's look at example 2.9. Yes. I think you start with the simple ones in the examples. These are actually kind of challenging. Can I erase? Anybody want to hold on to that? I was going to do one more on the board, then have y'all do that. I got it. 25. Tell you what. Yeah, y'all go to the board, and I'll give you a good board. Now we'll have some practice. Okay, draw a table with a steel ball rolling off of it horizontally. It's rolling off the edge of it. And it's, so you'll draw a horizontal arrow from your ball, like Maddie has there, and that is your initial velocity of 15.6 centimeters per second. That's VH in this case. Okay, VH is 15.6 centimeters per second. So if it's going horizontally and it rolls off the table, what's its initial vertical velocity? What's the VOV? 0. So in one column, make sure you set up a column for vertical and a column for horizontal. So 2 different columns. Okay, and so under the horizontal one, you'll say V sub O V is 0. And under vertical, you'll say VH. Did I say that wrong? Vertical is 15 point. Okay, your horizontal velocity is your 15.6 and your vertical is 0. Okay, yeah. And the height of the table is 73.66 centimeters. You could do that on your drawing, show how high the table is. 73.66. That also would be your DV. Yeah, your vertical distance.
What is it?
73.66 centimeters. And because the ball will be falling down, you should make that negative if down is negative and up is positive. Okay. So you can put that under your vertical column. I've got 2 columns. Okay. So it's going to roll off horizontal at this. So that goes over here. VOH. Be the 15.6. And then VOV, since it's not, doesn't have any upward motion or even downward motion when it first comes off, it's 0. Okay. And so its vertical motion is just basically free fall, right? And so vertical, you've also got acceleration. So put A, V is negative 9.8 meters per second squared. And this will be negative, so this will be falling. Yeah. And so we also need to convert all the meters too, by the way, the acceleration and vertical. Yeah, the horizontal, all you have is, at this point, is your horizontal velocity. Okay. Now, can you find anything from your vertical motion? You got some formulas that'll help you out? And you also need to convert to meters per second instead of centimeters. That shouldn't be too tricky. No, on this one you could, but it's going out straight. It's like 0. And so
So then we just
yeah. That's all the motion is horizontal. So that's why it's called the meters off horizontal. And the cosine of 0 is 1. And the sine of 0 is 0. That's the vertical. But you can still use it, you just have to know your angle is 0. Right now you're converting to meters, okay, meters per second. Okay, so we need to find a time. How about a time? How long will it take to fall? And where you have, so you're finding the final velocity. I think you can find the time straight up by using D equals D O V T. Wait, no, that's gonna be, hang on. You have D plus 1/2 A T squared. This is 0. So this whole thing becomes 0. And you have your acceleration, so you can find your time with this. It's going to be 2D over A, where the D and the A are negative. So y'all are finding the final velocity. Okay, that's fine. Okay.
You're looking at that for me.
So your distance bar versus the negative and then it's like the negative 9.8. Does that make sense? What is there? Yeah. Then oh, okay. It's better to put it all on the paper rather than if you're trying to save writing, it's better to write. So you're doing everything. This is one.
Cool one.
Yeah, so you can just look over two and divide by that. That should give you a time. What do you got, 0.3877 seconds? Okay, I'll just take that. Okay, then you can go back to your vertical side and put T over there as the same T on your vertical side. I'm sorry, no, you're on vertical. Your horizontal side, sorry, your horizontal side. So now you put time over here for your horizontal. You have the horizontal velocity. Now you can find the horizontal.
That's right.
Just but isn't that the time to fall from the end of the table to the floor?
Yes.
So how can you find that to the actually?
Because, okay, so it's going to be going like this, right? So it's got this horizontal motion, it's got this vertical motion. It's only going to have this horizontal motion this amount of time before it is. And that'll give you that.
Wait, I don't want to lie for the
Well, y'all are actually going to be doing this experiment, this exact experiment.
So
You're
is
gonna
it calculating from like the second it's on the table and it goes like
Yeah.
blue? Or
Second it leaves the table.
okay, I thought it was like table and then down.
No.
Okay.
Yeah, that's yeah.
So what are we doing?
Okay, so now you have D equals DT. So now you can find this D. You're trying to find the horizontal distance.
So for horizontal, it's only one equation? Like,
Yeah.
It's just, okay. That's what they want.
And then they grab you by the throat and choke you.
And you should come out. Yeah. Oh, okay, and if you convert that back to centimeters, look at that.
Doesn't matter.
I like how y'all did it two different ways and still came up with the same answer. No, it's science. So if you convert that to centimeters, it's about 6.05 centimeters. Does that seem about, if a ball rolls off the table, it would land about 6 centimeters away from the bottom?
No.
It's just, the distance is just meters. This was meters per second. And this was second, and the seconds canceled. Watch minutes. Yeah, and then if we convert it to centimeters, you'd have, what, 60 centimeters or 6? What you got, 0.6 or did?
Oh, I added an extra zero. Yeah.
Oh, it is
that's
60
fine.
centimeters, there we go. No, you were right.
Oh, I was.
I was wrong. Oh, you got 0.06. Okay, is it 0.06 or 0.6?
06.
Okay, then Brian? Did you just write it down wrong? You think? Yeah, 6 sounded better than 60.
Oh, okay. You're right.
06, 06. Yeah. Okay, you want to try another one? We got 10 minutes?
Oh, really?
Come on, it's fun.
I would have
She said it was fun.
better than homework.
Then watch that shit with the mark.
That was number 26.
Yeah, see, we're doing
Yeah.
homework.
Good homework. Let's try the angry man problem. Okay, so
No, it's not.
That's like your thing.
We're literally laughing right now, so shut up.
Angrily.
okay, so here you've got ground that kind of goes up, and It says, out in the middle of a parking lot, an angry man hurls his cell phone at an angle of 33 degrees above the horizontal. And then watching the phone's elegant parabolic trajectory requires 3.27 seconds of the man's life. The phone lands on a slight rise at the same height from which it is released. Okay, so he throws it and it goes up and it comes back down at the same level. See how he is?
Curve then.
Huh?
Oh, it's up a hill? Oh, okay.
Yeah, there was a slight rise, it says. And what angle was it? Okay, so an angle of 33. And the time that it takes to hit was 3.27 seconds.
What was that?
And they want to know, what is this velocity with which it left the man's hand? So you've actually got two things you got to find first. You got to find this horizontal component, VOH, and you got to find the vertical component, VOV, so that you can put them together to get VO. So let's separate our vertical and horizontal. Okay, make your columns. So what do we know? All we have is our time, right? We do know vertically we got A equals negative 9.8 meters per second squared. You can write something down, right? Seems like you didn't want this distance. You got a time. Oh, okay. And so, and you know the time vertical is 3.27 seconds. And when it lands, it's going to have a certain VFV that's actually equal to VOV. You believe me? The speed it was going up, when it comes down. Okay, well, let's look at it another way then. Let's look at half of the trajectory, half of the vertical trajectory. And let's say 1/2 of the time is how much? We're going to look at just the first half of this trajectory. Say it again, 1 point. Okay, and what is the final vertical velocity up here? 0. But then you find the initial vertical velocity using the half time. So VO equals VF minus AT. At a time of 1.635 seconds. So you see what we did there? Okay, see the equation we're using? It's the equation. Really, it starts out like this, VI plus AT. And we know we're trying to find this piece above. So, how do we know what we use? Because we're using the half of the vertical motion. It goes up, and the velocity up here is 0. And then the original is what we're looking for. And we're looking at just half of the time, so we're looking at the trajectory up and going down. So, minus, this is zero,
I think those are the
that's negative 9.8, and that's the half time.
Okay.
I didn't take
So
the
you're
roll
saying-
yet.
Yeah, oh, you do. Point six. This is one.
So what'd you get for that initial vertical velocity? 16.0230? Y'all got it? Okay. So what can we do horizontally? We need to know how far off it, how far around it is. The same height. I guess. Horizontal, we got time. See, we don't know how far out it went. Well, we're gonna have to stop at this point because of the time, so you need to, I need to figure out what the next step is on this one. I remember it wasn't too tricky.
Okay, so can we have to do the first?
Huh?
We have to find the vertical component.
We found, that's what we found right here. Now we need to find the horizontal one. And we know how much time it was going, but we don't know the distance. And we only have that one equation. So I'm gonna have to figure out what the deal was. Okay, so we'll stop, we'll pick up there tomorrow. So y'all can clean your desks off and get ready to head out. Oh, that's right. Okay, well, I'm gonna stop the recording. Great.